Hey everybody, I remember when I took in high school deductive logic, and it would be like if A implies B, like Barney goes to the store and Barney buys eggs, and then B implies C, so Barney buys eggs, Barney's going to make an omelet. And so therefore, if A implies B and B implies C, you can say that if Barney goes to the store, Barney's going to make an omelet. And so that's called the chain rule. And this is kind of what we're doing today with Hess's Law. And by the way, this never works in sports. Like, oh, if the Bills beat the Raiders and the Raiders beat the Chiefs, then the Bills should beat the Chiefs. Nope, that didn't happen. And sports don't follow the kind of predictability that science does. So, and maybe if someone go into the store this might be a crappy example too. Let's talk about Hess's Law. Howdy everybody, howdy, Mike here, and we are going to talk today about Hess's Law. I mentioned there, chain rule, that was one of my favorite things of deductive logic, and this is not much different. And so we have the concept of multi-step reactions, and what happens is you can add them together. So for example, we could say, well, carbon's going to put on 2 oxygens and become CO2, but we could break it down into multiple steps where we're putting 1 oxygen on at a time. And so what happens is you've got this first step where the carbon goes to make carbon monoxide, and that has a certain delta H. And then you have a second step where the carbon monoxide puts on an oxygen and then becomes CO2. And then what you could do is we could say, well, let's add these together and treat it like it was one step. And that would be carbon plus O2 goes to make CO2. And the delta H's would then add. And you'll notice that these oxygens added, that carbon monoxide canceled. So it's very much like what you could do with algebraic problems, in that what you do to the equation you have to do to the delta H. So I added these 2 reactions together, and the delta H can be added together. So of course it isn't, but if we were just speculating that there's a third reaction that we've never before witnessed to happen, we could predict its delta H and extrapolate from a set of 2 equations, we could extrapolate a third. That's how most of your delta H tables were actually created, and this is called Hess's Law, the ability to do that. And I never know where to put the apostrophe. If there's another, I think I did it right. All right, but that's why I'm a chemist, because I suck at grammar. Yeah, okay, so other things you could do to a chemical reaction, I could multiply them. So for example, let's say we have CO2 being formed from carbon and oxygen. If I was to multiply that reaction by just 3, I just pulled that out of my, you know what, just if we were to have to multiply 3 moles of CO2, then the delta H would be multiplied by 3. It makes sense. Forming 3 moles of CO2 would create 3 times as much heat, or 3 times as much heat would be liberated. Similarly, you could flip a reaction. So the nice thing about thermodynamics is it makes sense. That is, that if you have a forward reaction that is exothermic to the tune of minus 393 kilojoules, if I were to turn it around, what was exothermic is now endothermic, and specifically the same amount of heat is involved. It's just flipped. You can think of that as multiplying it, the whole thing, by -1, where the delta H would just change sign, but final minus initial would get flipped, which means products and reactants would get flipped. And now, if you employ these tactics to some sort of equation that you want to know the delta H of, but you can't maybe pull off measuring it from a calorimeter, then you can theoretically calculate it. And these are kind of like puzzle-like problems that are, I would say, sometimes could be possibly even enjoyable. Did I just say that? Or am I just selling it? A little bit of both. I don't mind them. They're kind of like little puzzles. We're going to do an easy one, an easy problem using Hess's Law next. Okay, here's a beginner problem. Now, what happens here is you're always given some reactions, but then you have like the target equation, which you want. And there's a strategy for doing this, and what you do is you go ahead and look at the equation they're asking for, and they'll give you a whole bunch of other delta H's with equations, but I want this one on top here. So what I'm going to do is I'm going to scan through it, and I'm going to say, okay, 2 carbons, where can I find carbon? I hope you don't mind, I took the subscripts off, so you realize that carbon is a solid down here too. It just cluttered things up, so I took it off. We could always put it back later. So looking at what I've been given, I only find carbon in one of the 3 equations. There's no carbon there, there's no carbon there. Carbon's here, but it's not present with a coefficient of 2. So what I'm going to do is I'm going to go ahead and say, give that a coefficient of 2. Now notice how I'm putting the parentheses on around both the equation and the delta H. And so what's going to happen is I'm going to go ahead and multiply that by 2, but I'm going to skip to the next thing. I'm going to say, okay, here's hydrogen, and there's hydrogen only in one place. That's why this is kind of an easier one. There's not 80 things in 70 different places. So hydrogen is actually, I'm kind of cool with just leaving that alone the way it is, because hydrogen's on the left with a coefficient of 1, hydrogen's on the left down here, it's only present in the 3rd equation. Here's C2H2, acetylene, and that is here in one equation, but it's on the wrong side. So I'm going to have to flip that one. And then what I like to do, folks, just to check, just to protect myself from myself, I like to write this whole dang thing all over again. And so I even like to make sure I don't goof up by putting the arrows all on top of each other so I don't confuse what's on the left and right. So what I'm going to do now is I'm going to flip this first reaction. It's going to be 2CO2 plus H2O goes to make C2H2 plus 5/2 H2O. Now look, that 5/2 H2O does scare me a bit. But what happens is if you do this right, the thing that's in like 3 different places, or in this case 2, that will hopefully cancel if you do the right thing. And if it doesn't, then they gave you the wrong information somehow. Now all that's going to do is make delta H positive 1299.5 because I flipped it. I'll put kilojoules on in the end, all right? The second one I'm going to have multiplied by 2, so 2C plus 2O2 goes to make 2CO2. And the delta H is going to be doubled from 393.5. 393.5 times 2. Doesn't change sign because I didn't flip nothing. So that's going to be positive 787 over here. The third equation I didn't touch, but I'm still going to write it again. And then the reason I'm writing all this stuff again is I want to make sure that those O2s canceled and that I get what I wanted. So let's see, delta H here doesn't change. It's still the same thing, minus 285.8. And I'm hoping that when I do this, everything's going to cancel perfectly. And so let's make sure that it does. And then I get the equation that they asked for. So, all right, first of all, these waters cancel, which is great because they're not present in the equation that they want. My 2 C's are going to come down here. I'll write solid in again. These 2 CO2s cancel, which is cool. And then, oh, here's my O2 problem that I have. So you got to watch out. 5/2 O2s there. And this is just like saying 4/2 O2. You can change it to that if you want. So this would be 5/2. 4/2 plus 1/2 is 5/2. All these O2s cancel like I told you they would. And we're now able to celebrate because we got the equation that they wanted. Now all I got to do is carefully add up my delta H's, and that will be the answer, because what they really want is the delta H. Watch your signs. I'll double check that the one I flipped changed signs, and it did. So 1299.5 positive plus 787 minus 285.8 is 1800.7. All right. Oh, you know what I did? Yeah, I almost, look what I did. Now, you know, I'll tell you why I found that out. And I almost didn't. I'm gonna revel in my goof up, because I'll tell you why that should be a minus 787. 1299.5 minus 787 minus 285.8 is positive 226.7. How did I catch myself? Well, first of all, I just double checked my signs, and I noticed that when I didn't keep the sign negative here, I was just in a hurry and I wrote it down. But I happen to remember that acetylene, that's a delta H of formation right there, folks. And I happen to know that the delta H of formation acetylene is pretty positive, because it's not a very stable compound. But when I saw positive 1800, I'm thinking, hey, this ain't TNT like the last problem. It's not that unstable, and it's also a mole, doesn't weigh much. So I thought, that's weird. And then I spotted that I did not keep my negative sign from one step to the other. All right, I'm going to shake that one off, because I got to get better, because the next one we're going to do is going to be skill level expert, and then we're going to be, what we call in science, done for the day. And you're not. You're going to go practice a whole bunch more, but this will be a tough one coming up next. All right, now folks, this one's got a lot going on in it. And then what they did is they gave you the equations first and then gave you the target equation second. You just remember, you're always looking to the target equation. Okay, we want to find the delta H of that. Now, by the way, if you're lucky enough to be given one like this, where you say, that's the delta H of formation from the elements of CO2, and you go look in the chart and you say, that should be my solution should give me minus 393, because that's what's in the table. We'll hope we get something like that. But you know, that'll help us know what the answer is. Now, here's what we got. We got carbon here, and I'm going to go find carbon only in one place, and it's not in this equation here. It's not in that equation there. There's a lot of strontium that's got to cancel, but I'm going to worry about that later. Just keep your eye on the prize. I'm going to look at carbon here and say, there's a carbon there. It's on the wrong side. It should be on the, when I want to get done with adding these reactions together, I want carbon to be on the left, so I got to flip it, but I also got to divide it by 2. So this is minus 1/2 through everything too, not just the reaction. The delta H is going to have to flip sign, I'll remember to do it this time, and then be multiplied by 1/2. O2, I got it in a couple different places, and that scares me. So what I'm going to do now is skip it for now. CO2 is a little bit surer of a bet, because I know it's there on the product side, it's on the reactant side here. So now I got to flip this one. And then I'm not sure what to do with the rest of this. So here's what I would suggest doing. Let's go ahead and do what we're going to do to the two reactions, so that we can get a clearer picture of what to do with the third. And the third one has got to make sure that there's O2 on the left, but you know what? I'm going to have O2s on the left because of what I do to this equation. So maybe I just have to do what I have to do to this second equation to make all that crap, the strontium and strontium oxide and the strontium carbonate, I got to make that all cancel. So what I'm going to do is I'm going to go ahead, rewrite these two equations. Now I'm going to need a third equation. Once again, I like to put my arrows all in a line so I don't goof nothing up, all right? And so I'm going to rewrite this one the way I need to. Strontium carbonate goes to make strontium oxide plus CO2. And then, easy enough, I got to flip its sign. And I'll remember to do that this time and not daydream like last time. I'm going to go ahead, doesn't matter what order you do it in, we're going to add them all together anyhow. And so I'm going to go ahead and do this one now. It's a little trickier because now what I'm going to have is just a strontium carbonate on the right. All right, I'm going to have to, that 1/2 times 2, I'll do my delta H later. Then on the left is going to be 2 strontiums plus, not 2 strontiums, Mike, 1 strontium, because I have to multiply it by 1/2. 1 strontium plus 1 carbon plus 3/2 O2. And then the delta H is going to be negative, but also 2440 divided by 2. So minus 1220 kilojoules. Now, what to do with this equation up here? And I just spotted it, what I need to do. Because of the way I wrote this, I'll go ahead and do it now. My strontium carbonates, which aren't in the equation they want, they're going to cancel. So I don't have a strontium carbonate problem because this second equation up here doesn't have strontium carbonate in it. I do have a strontium problem where I have strontium on the left from this equation, and strontium's got to cancel. So I need to have 1 strontium on the right when I write this equation, and then I'm just going to hope for the oxygens to take care of themselves. And same thing with the strontium oxides. Actually, I could spot what I need to do with the strontium oxides. That needs to cancel. So for both of those reasons, I need a strontium oxide 1 on the left, and I need a one strontium metal on the right. This guy needs to be multiplied by 1/2, but not changed in its direction. And so this whole reaction, the third one, is just going to be to cancel stuff. And so that would be 1 strontium oxide goes to make a strontium plus 1/2 O2. And then what would happen is the delta H would now be still positive, but 1/2 of 1,184. Positive 592. Sorry, my handwriting is all kind of jacked up because I'm reaching around a camera tripod. So now let's keep track of what cancels. Strontium oxide cancels, groovy. Strontium metal cancels, great. And when I'm done with this, I will get, okay, now let's check out my oxygen problem. 1/2 O2, 3/2 O2. So what'll happen is 1/2 of the O2s will cancel, and it'll become 2/2 O2, which is the same as writing a single O2. So that was a tricky one with fractions and everything. What survives this whole thing is my carbon plus my oxygen. Now comes the finale, when I have to then add up my delta H's. So positive 234 minus 1220 plus 592 minus 394. And actually, let's give it its units. Kilojoules per mole. Oh, and I can make it look nice and professional again with my subscripts. And that is making me feel relatively good about myself, which doesn't happen that often. But because what's going on there is that's about what the table tells you. Now, you would say, well, why are we doing these things that are in the table? Yeah, you got a good point. The whole point of using Hess's law is we can go find stuff in the table and then extrapolate a second or third or fourth reaction from a bunch of different reactions to predict what the delta H would be. And then what a scientist would do is go say, okay, now let's verify this. We'll go put this stuff in a calorimeter and do the reaction, if you can, and then measure the delta H. Or if you can't put it in a calorimeter, because a lot of these things aren't easily produced by just putting two reactants together and making that compound. A lot of these things on this table, folks, were figured out by Hess's Law. And so there you go. Kind of nice, neat little puzzles that you can do in your own time instead of your Sudoku or whatever. It's empty square, or whatever. Folks, I will catch you later. Cheerio! Frankenberry. Count Chocula.